All right, so similar triangles, or really just similar figures, but we're going to focus on triangles here. Similar triangles are, you can essentially imagine it as just two different triangles that have the exact same angles, which means that they're the exact same shape, just one is larger than the other. So we say here two triangles are similar if their corresponding angles are equal, which means the ratios of their corresponding sides are equal. Which again, what does that mean? Well, like again, in its essence, like what we see here, these are two triangles. But one's bigger than the other, but they're the same shape. So if they're the same shape, that means whatever angle this is right here, angle N, this must be the same thing over here, angle J. If they weren't the same angle, these wouldn't be the same shape. And angle P must be the exact same as angle K. And angle M must be the exact same as angle H. Because again, if their angles were not the same, these shapes would not be the exact same shape in terms of the angles on the inside. But one of the triangles is definitely bigger. So they're different triangles, but they're related to one another. And we say they're similar. And that little symbol we see there, that sort of wavy line, that's a symbol for similar. So I'm saying triangle MNP and triangle HJK are not the same triangle, but they are similar, which means they're related to one another, which also means the ratios of their corresponding sides are equal. So what does that mean? Well, for example, if I just look at this, if I look at side MN and I look at side HJ, they're not the same length, but they correspond to one another. They're the same side of these similar triangles. And the same way NP corresponds to JK. They're not the same side, but they're related to one another. And again, right here, MP and HK are different sides, but the different values, but they're related to one another. They correspond to one another, we say. And for example, if I just pick a side, I don't know, MN, the one I've highlighted in yellow over here, that's 4. And if I compare that to its corresponding side, HJ, which is 10. Well, if I go 4 divided by 10, I will get an equivalent fraction if I do a different pair of corresponding sides in the same order. For example, if I go 6 to 15. And 4 over 10 is equivalent to 6 over 15. They are equivalent fractions. And if you're not sure how to prove it, you could decimalize each. You'll get 0.4 for each of them if you decimalize it, if you go top divided by the bottom. Or you can reduce them both to 2/5. Either way, they are equivalent fractions. And the same thing if I go NP over JK. If I go 7 divided by 17.5, it's less obvious, I'm sure. But if you go 7 divided by 17.5, you'll get 0.4. All these fractions here are equivalent. And that's really what this last line means. The ratios of their corresponding sides are equal. And I can find tons of combinations of this. For example, if I go this side divided by this side, I'll get the same ratio if I go this side divided by this side. And I'll show you. If I just look at this, if I go 4 centimeters over 7 centimeters, I'll get the exact same ratio if I go in the same order 10 centimeters divided by 17.5 centimeters. In this case, if I don't blame you if it's not obvious that these two ratios are equivalent, but if I go 4 divided by 7 on my calculator, I get some messy decimal, and I get the exact same thing if I go 10 divided by 17.5. Any order. All right, so there's a lot of combinations here. So how can we use this? Well, once we know triangles are similar, therefore we know there's all these combinations of ratios, we can use that to figure out missing angles, or missing sides. Missing sides, actually, more. And so let's look right here. Find angle T. So I want to find this angle right here, and the side ST, which is this side right here. Knowing that these two triangles are similar, and that little squiggly sign there tells me that these two triangles are similar, which means they are different triangles, right? One is clearly larger than the other, but they have the same shape, which means they have the same angles on the inside, which means if I look at these two triangles, if this angle from here to here is 110, this must also be 110 degrees. And if this angle from here to here is 40, this angle over here must be 40 degrees. So angle T I can find really quickly by remembering the important fact that all triangles have interior angles that add to 180 degrees, which means 110 plus 40 plus something equals 180. Again, that fact is true to all triangles. So I can figure out angle T really quickly. Angle T must be the same as just 180 degrees minus my other two angles, minus 110 and minus 40 degrees. And so in this case, I can see quickly that angle T is exactly 30 degrees, which means so is angle Q in the other triangle. They must have the same angles. All right, so to find angle T, I didn't need any special triangles in terms of finding proportions or anything. I really just needed to know how these angles compare to one another, and then remember that all triangles have a sum of interior angles that add up to 180 degrees. That's it. How do I find the length of ST? For this, I need to take advantage of what I was just talking about in the last question, these proportional ratios between different sides. So I have a lot of ways I can approach this. But for example, if I look at these two triangles, I'm going to highlight the sides that are corresponding. So 2.5 corresponds to what we're trying to find, ST. And 2 centimeters corresponds to this 5 centimeter side here. So that means I can say that, for example, 2.5 centimeters over side ST, which I don't know what it is, whatever that ratio is, 2.5 divided by ST in that order. ST being what we're trying to figure out right there. I know that must be the same as 2 divided by 5. And there's other combinations, but again, it doesn't really matter. As long as I find one ratio like this, I can now figure out what that side ST must be. And so if I look at this, 2.5 divided by ST, and if you don't like ST, you can put an X there if you want, right? If ST kind of throws you off, sure, put an X. There you go, a little more familiar, but same idea. And then just call this, instead of a question mark, call this X. So what is X? Well, and sometimes you can kind of tell just by looking at it, but if you're ever not sure, we can cross multiply, which is really helpful for expressions like this. So in general, anytime we have one ratio equaling another, one fraction equaling another where we have a single unknown value, there's always lots of approaches, but one that's really quick, and therefore I think it's useful to talk about this point, is what's called cross multiplying. And so in this case, if you look at these fractions here, if there's only one unknown, there must be a pair of numbers that are diagonally across from each other that we know. In this case, it's these two right here. So 2.5 and 5, that's the only pair of numbers I know that are diagonally across from each other. So what I do first, and it's very quick, is I multiply those together. So I go 2.5 times 5. And then I just take that and I divide by the one value I haven't used yet, which is the 2. And this will tell me the value of X. Always. And there's other approaches as well, but in this case, it's always, when we have these ratios set up, it's quite nice like this. And so when I go 2.5 times 5, I get 12.5. Divide by 2, I get 6.25. So that X is 6.25 centimeters. That's it. There's lots of options about how you can solve this. And sometimes I'm not a big fan of cross multiplying in terms of just, it's students tend to misunderstand how to use it. But anytime you have one fraction equaling another with a single unknown, like we have here. If I had 2, that's a highlighter. If I had 2 over 8 equals 1 over something, I could use cross multiplying here. Although in this case, I think it would be easier just to realize, well, 2 is a quarter of 8, so 1 must be a quarter of 4. So X must be 4. So like I said, sometimes you can just see it. But also, what will always work is find the pair of numbers that are diagonally across from each other, in this case, the 1 and the 8, times them together, and then divide by the number that's left. So equals 4. Again, it always works. Just don't always use it automatically. OK, either way, though, finished this question a while ago. So let's look at the last one. Find the length of side MN. So I have this here. I want to find the length of that side there. So the way I want to approach this is realize that, or think of it as two triangles kind of on top of each other, or nested in one another, we say. And so if I look at this, maybe I'll draw one triangle M or K, MNK, however you want to call it. And I also have another triangle that is similar to it. right, the triangle I'm tracing out in red, is larger but has the same angles as a smaller one. So this may be a little easier if I actually draw these two triangles separately. Okay, so I have, I'll leave the smaller triangle kind of drawn there in orange. But sometimes it's easier just to literally draw the second one separately. And what I know with the big triangle, I know it's 36 meters on the bottom. And I know it's 40 meters across the side right here. Right, 30 plus 10. And so I also know this 36 meters corresponds with the side I'm trying to find, MN. Or if you don't like MN, call it X, or call it Y, but you also just call it MN. And so now I can look at these two triangles as being two completely separate triangles. And so now I can make my corresponding sides. And one option is to say, and again, I'll just do a few different options. I can say 40 over 36. I'll write that down. 40 divided by 36. In that order, must be the same as 30 divided by x. Notice how my corresponding sides all match up. And so now I can focus on this. And I have a lot of options. I could reduce the 40 over 36 first. But again, I can also always just cross multiply. So in this case, I'll go 36 times 30. And then take all of that and divide by the 40. And that will tell me x. So if I go 36 times 30 right away, I get 1,080 divided by 40. I get 27. And so 27 is x, or the length from m to n. So I'll just formalize it and say, therefore, mn equals 27, and the units were meters. So like I said, chances are drawing the two triangles separately made it more clear how to approach this.